Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to chapter 9 lecture. As usual, there will be two lecture recording for chapter 9, part A and part P. Chapter 9 is basically continuation of what we covered in chapter 8. Um, in particular, we will focus on molecular geometries and bonding theories in molecules as well as polyatomic ions. As usual, I'm just going to break down or define the title or the terms used in the title, the molecular geometry and bonding theories. Molecular geometry is basically a three-dimensional arrangement of atoms around uh, the central atom. We're gonna look at that, but when you think of three-dimensional arrangement of atoms, this is defined by molecular geometry. Bonding theories, there are two types of bonding theories, but before that, the arrangements include general shapes of the molecules, bond length, and bond angle, okay? These three arrangements include the general shapes, okay? Bond length and the bond angle. Bonding theories, there are two. One, valence bond theory, which is states that chemical bonds are formed when atomic orbital overlap. When atomic orbital overlap constitute what we call valence bonding theory. There is a molecular orbital theory, which is treatment of atomic orbital in such a way that the chemical bond in a molecule is defined by electronic structure. Okay, we will see that. Without wasting my time, let's see part A. We will look at the molecular shape of valence shell electron pair repulsion models, which is used to define the structure of or predict the structure of a molecule. Look at the molecular shape and molecular polarity, covalent bonding and overlap before we shift on to our part P, starting from section 9.5, 9.6, 8 to 9.8, 9.8. So when we talk about molecular shape, typically you may have seen Lewis structure for H2O represented, or just the structure of H2O given as H, single bond, oxygen, single bond, in a linear manner. This is oversimplified. The actual shape of what a molecule is pear shape, where we have oxygen, there is and hydrogen and oxygen. This is the molecular shape for H2O. Now, what really determines this shape of H2O? All right, we will use the Lewis structure to predict, and of course, by now you should be able to draw the Lewis structure for molecules or polyatomic ion, right? You should be able to define the bonding electrons and non-bonding electrons. We will use those, we will use the knowledge of Lewis structure for molecule and polyatomic ion to predict the molecular shape. You don't need to memorize, for example, here, you don't need to memorize the molecular shape for CO2, for sulfur dioxide, sulfur trioxide, nitrogen trifluoride, or chlorine trifluoride. Suppose you are given other molecules other than the one you see on the PowerPoint slide on section 9.1, how will you predict the molecular shape. There is a table I'm going to walk you through, and I will allow you to use in the exam to predict. First of all, what are these AP, AP2, AP3, AP3, AP3 means? In conjunction with the Lewis structure, we will use this general formula for predicting the shape of molecule or polyatomic ion. And this is how this works. One, all right, let me show you the PowerPoint slide. So if we have this general formula A, B, X, E, N, all right, we can divide, all right, we can divide the terms here. A, this stands for the central central atom. What is at the center? Central atom. And Bx right here, this stands for number number of external, all right, external atoms hooked up to the central. We'll see what central means, what is at the center. For example, in carbon dioxide, carbon is at the center. In sulfur dioxide, sulfur is at the center. Sulfur trioxide, sulfur is at the center. And external atom, in this case, the oxygens for the first three molecules, or fluorine in the last two. So external atom stand for. So this is P3, all right? Because of the three atoms hooked up to the central. These are three. If we are four, it's gonna be P4. And then En, all right, here En stand for number of lone pairs of electrons, low number of pairs of electrons, all right? Low number of pairs of electrons. So if we add lone pairs of electron on oxygen, all right, we will indicate how many, if there are two, not two electrons, if there are two dots on the central atom, that counts as a single. This is the general template. I will allow you to use this table here. If you look at the last column I created here, AP2, AP3, AP3 to E1, these stand for two external atoms, and there is a single lone pair of electron, lone pair, that is one pair of electron on the central atom. There are no pairs of electron for external atoms. There are three external atoms with one lone pair on the central atom. For this, two external atoms on the central, hooked up to the central atom, and two lone pairs of on the central atom. We will use this general template here to predict the molecular shape. I just wanted to show you so that when you get to the drawing of the Lewis structure, all right, you have to remember the general formula. You have to remember the general formula, AP2 EX. Let's say, for example, here, how do we know that this is linear? How do we end up with that? So if I draw the Lewis structure for, all right, Lewis structure for CO2, here Lewis structure for CO2, remember rule number one, count the total number of valence electron. Carbon is in group 4A, it has 4 valence electron times 1 carbon, so we have 4 electrons. Oxygen is in group 6, so there are 6 valence electrons times 2, we have 2 valence electrons, right? So 12 electrons. Adding up these, we end up with 16 valence electrons. I'm doing carbon dioxide in order to come up with a shape. So having said that, the central atom, by the way, the central atom is always the atom with more or most bonding side with the more single dots, not pair. So here, oxygen are external atom. This is the structure of, the skeleton. Here is rule number 1. If you want to recap drawing the Lewis structure, rule number 2, draw the skeleton. So we have used how many? We have used 2 electrons here, 2 electrons here. So minus 4, we are remaining with 12 electrons remaining. So there are 12 electrons remaining. Out of the remaining electron, the external atom take first priority in satisfying the octet rule. So oxygen needs 6, this needs 6, this needs 6, this needs 6, this needs 6. All right. Do the inspection, make sure that each atom in the molecule satisfy the octet rule. And if I look at the carbon, we need to make double bond on either side. I'm just fast forwarding the Lewis structure concept, which you should know. So at this point, we have the Lewis structure for CO2. It is of this type, A, B. So if we use this, A, P, 2, when there is no lone pairs on the central atom, we just leave it as AP2. This is now when you go back to your table and say, okay, what is the, all right, what is the structure for C, what is the structure of AP2? It is linear, which means linear, and there is what? Linear with 180. This is the bond angle. You will also have to remember the bond angle. Remember the bond angle between external atom. Bond angle is the bond formed between external atom and the central atom. So for CO2, it is linear. For CO2, it is linear. I want to highlight two things, two types of shape. We have what we call here types of shape you may be asked to state in a molecule. One, electron domain geometry, and then there is the, here we abbreviate this, by the way, we abbreviate this as, all right, we abbreviate this as G, electron domain geometry. And then there is the molecular what? Molecular geometry, molecular geometry, and this is MG. You may see this terminology in the exam that define or state the electron domain geometry and the molecular geometry. In the handout, right here, all right, in the handout, there is the geometry here. That is geometry of the atoms. This is the molecular geometry. This is electron domain geometry. That means looking at the domain of electrons around the central atom. So that when you get there, you need to know this includes all the lone pairs. This does not include the lone pairs. It only look at the atoms. So we will see this how we end up with the definition of different shapes, all right? And what determines the shape of the molecule? We have stated that it's the bond angle, which is basically the angle between, or the angle formed by the central atom with the external atom. The angle between external atoms and the central atom. This is what defines the bond angle. The bond length as well define electron pairs also define the geometry in the sense that those unshared lone pair can repel. Remember, electrons are negatively charged, and if we have lone pairs, they tend to repel one another. They repel, stay as far as possible from one another because of the negative charge. So electron pairs are as far apart as possible. This allows predicting the molecular shape. So what predicts the shape is the electron, basically the electron charge, which is negative, and they tend to repel one another. We use what we call Fallon shell electron pair repulsion model to predict the shape. We use Fallon shell electron. This is abbreviation. You should know that. And you see this on the handout. It is Fallon shell electron pair repulsion model, which you choose to predict the shape of the shape of the molecule. And this is grounded. This model is grounded on understanding the Lewis structure. Let's see. What do we mean by domains? Domain is where the electrons are. And when counting the domains, double bond is one domain. One misconception student make is thinking that double bond constitute two domains, triple bond constitute three domains. No, a domain is just where the electrons are. And I want you to look at how I'm counting the domain in this hypothetical molecule. Double bond here is a domain. So this is one domain, right? Maybe I can zoom this out. This is one domain. This is one domain. This is one domain. This is one domain. So lone pairs of electrons constitute a domain. Single bond, one domain. Triple bond, one domain. Single bond, one domain. So the central atom in this is A, and it has 4 domains. So the 4 here is this 1, 2, 3, 4. We have 4 domains. We have 4 domains. Here is a good learning check to see if you have mastered the concept of valence electron pair repulsion model. In counting the electron domain geometry around the central atom in valence electron pair repulsion model, dash is not included. We just went through that. A non-bonding pairs of electron on the central atom. Remember here, central atom, we do include, so A, we include that. Single covalent bond, we include B. Core electrons, we don't look at the core electrons. A double bond or triple bond, they are, so the correct answer is C. In this case, we do not count. The correct answer is C. We do not count the core electrons. We do not count the core electrons. So that is all about the domains. And let's move on to section 9.2, financial electron pair partial models to predict the shapes of the molecule. The best arrangement of a given number of electron domain is the one that minimizes the repulsion. If you look at the first picture on my right, this represent domain of electron, and they tend to repel one another using the analogy of a balloon. The electron pair repulsion models, all right, they repel one another. Electrons tend to repel one another in the molecule because they are negatively charged. I have earlier on given you two types of domains. There is electron domain geometry, we define the shape, and then there is the molecular. What's the difference between the two? We'll look at the table momentarily. Electron domain geometries are based on electrons around the central atom, and to determine the electron domain geometry, count the total number of lone pairs, single, double, or triple around the central atom. I will use sulfur dioxide, for example, to show you how you end up with the counting of the domain and probably predict the shape. First of all, you need to draw Lewis structure. Lewis structure. Lewis structure for molecules. And in this case, we're gonna have only sulfur dioxide. So sulfur is in group 6, oxygen is in group 6, and we have 2 of them. So here is 12 electrons plus 6, we have 18 electrons. Rule number 1, count the total number of valence electrons. Rule number 2, draw the skeleton. Sulfur is at the center, bonded to 2 oxygens. We have used 2, all right? We have used 4 electrons. 18 minus 4, we are remaining with 14. And if each oxygen takes 2, we remain with 2. The 2 electrons goes on the central atom, but sulfur does not satisfy the octet rule. So we can make a double bond on either side, any of, not both, but one side. All right. And each atom in the molecule satisfies the octet rule. So if you look at the central atom, we count the domain 1, 2, 3. So for this electron, therefore, electron and molecular geometry. In electron in domain geometry, we count the 3 here. 1, 2, 3. So it is A, 3. But for molecular geometry, we will look at A, P, 3, AP2, sorry, it's AP2. This is AP2, A1. In order to define or state electron domain geometry and molecular geometry for sulfur dioxide, like that molecule, through the Lewis structure, pay attention that the octet rule is satisfied on the central atom, and then use the Fallon shell electron pair repulsion table to predict the shape. In this case, I will use the table here and see for, all right, for electron domain geometry here, what we will do is, let me minimize this. For electron domain geometry, I wanted to show you here, all right, side to side. If you look at the electron domain geometry, it is AP3. AP3 electron domain geometry is trigonal planar, AP3, all right? That means looking at the electron. So you cannot have same geometry for electron domain geometry as well as molecular. So for here, this is trigonal planar. How did I end up with this? It's because of AP3. Look at the column. No lone pair. So for electron domain geometry pairs for AP3, it is trigonal planar. But AP3E1 for molecular or geometry of the atoms is paired or fission. So here, this is paired fission. So we're gonna have paired or fission. So the shape will assume this. So if I was to draw molecular shape, this is oxygen, and this is sulfur, okay? And indicate the lone pairs for dot structure. And of course, you'll have 4, and then this one will have 6 dot pair. You're not gonna have the dot pair. For molecular shape, this is pan shape. We'll say pan shape. So there are 2 types of shapes you will be asked to, all right, you'll be asked to state. Either pan shape or either you are asked electron domain geometry or molecular. Please make sure you are familiar or well versed with the Lewis structure for molecules or polyatomic ions. So this is the table being referred in the slides that in the text. Table 9.1 electron domain geometries is a function of number of domains. So for two domains around the central atom, right? We have electron domain geometry and molecular. All right, molecular. These terms, you need to memorize this, that if you have three domains, if you have four domains, these are the geometries, the terms associated with each domain. What do I mean? When we say trigonal planar, how many domains around the central atom? This is a domain, this is a domain, this is a domain. And remember, these are electrons. For this one domain, there's another domain, there's another domain. And that is why it's trigonal planar, and it's 180, 120 degrees, 120 degrees. This is the bond angle. Do you need or are you required to memorize that? Be given that, but what I want you to learn is how you come up with the conclusion as linear tetrahedral based on the number of domains. For 5 domains, trigonal pyramidal. For 6 domains, octahedral. You need also to know the angles. You need to know the angles. These are the key terms used to describe electron domain geometry. We'll see the molecular shape, okay? Molecular shapes, we'll also use the same terminology, but remember, in all this, you need to draw, or you should draw the Lewis structure for molecule or polyatomic ion in order to come up with a conclusion as trigonal. I will allow you to use the valence shell electron pair repulsion table in the exam. I'm just going to include that. Yours is to learn how to use these tables to come up with the correct number of, not number, but the correct definition of the shape. Okay, so let's see. These are the domains. 2 domain. All right. 4 domain, 3 domain. If you look at the 3 plus 1 is 4. So here, what you see here, these are 3 domains, 2 domains, 3 domains, 4 domains, 5 domains, and then 6 domains for octahedral. Let's see, for linear electron domain geometry, CO2, no non-bonding pair. So it's just AP, that's what I showed you earlier on here. It is AP2, there are no non-bonding pairs on the central atom. So there are 2, use linear. Learning check, let's see the typical question in an exam. Here is a typical question in an exam or quiz. The molecular geometry for CS2 is dash linear pen tetrahedral trigonal or T-shape. In this case, you don't need to memorize. Maybe somebody might think that, oh, do I need to Google out and memorize that? No, all you need to know is how do I go about drawing the Lewis structure. So draw a Lewis structure for CS2. Remember, the central atom is the one with the most bonding side or the less electronegative. So one, we need to do what? Count the total number of valence electrons, total number of valence electrons. In this case, carbon is in group 4 times 1 is 4 electrons. Sulfur is in group 6, so there are 6. Sulfur has 6 times 2, this is 12 electrons. So this will give us 16 valence electrons, 16 valence electrons, 16 valence electrons. Once we know this total number of valence electrons, rule number 2 in drawing the Lewis structure is draw the skeleton. Draw the Lewis structure for draw the skeleton of the molecule. So here, carbon is at the center, bonded to 2 sulfur and sulfur. All right. We have 2 sulfur bonded to carbon. Out of the 16, we have used 4. So subtract 4. These remain what? Remain from 16 minus 4 remain 12. So here we put 6, 6, 6. 6, 6, 6. So minus 12, 0 remaining. So we need to make a double bond here, from here, make a double bond on either side so that carbon satisfy the octet rule. So I'm just gonna have here what? 4 electrons. I've used 2 to make the double bond. I've used these 2 electrons here to make a double bond. These 2 here to make a double bond there to give us that. So if I look at the formula using now the general formula, this AP2, AP2, which is linear. So our correct answer is A. You don't need to memorize, okay? All you have to do is draw the Lewis structure for the molecule. You should be able to identify the central atom. In this case, the least electronegative, the one on the first column, or the one with the most bonding side. That means they have a single electron to share. So nevertheless, the correct answer is A, linear for carbon disulfide. For 3 bonding sides, all right, 3 bonding sides, if you look at the electron domain geometry, whether including the lone pairs, you see the lone pairs, 1, 2, 3, there is a lone pair here representing that. But if you look at the side, the domains, we have 3 domains. 1, 2, 3, 1, 2, 3. Trigonal planar expansion. So know the molecular geometry as well as the electron domain geometry, how you define. It's not always that electron domain geometry is the same as molecular geometry. This is molecular geometry. which only look at the connection of atoms. This and this is better. We don't look at the single bond, a single electrons here representing for trigonoplanar, this is the paired shape. The molecular geometry for sulfur difluoride, I don't know if it's gonna be linear, so don't think that always when you have, all right, when you have H2O and anything with two external atom bonded to the central, you use linear. No, you have to do your work. It may be linear, it may not, I don't know. But for this, let's see, sulfur dioxide, sulfur difluoride. Sulfur has 6 electrons, it's in group 6. Fluorine is in group 7, times 2 equals to 14. If I add everything, this will be 20 valence 20 valence electrons. So we need to know the total number of valence electrons. Rule number 2 is draw the skeleton. So if I draw the skeleton, sulfur is at the center. Fluorine, in this case, they are our external atoms. Out of the bonding electrons, 4, we have 2 here, we have 2 here. So we have used 2 in bonding. We call this bonding electron. Remaining 16 electrons remaining. And in this case, external atom take fast priority in satisfying the octet rule. It takes fast priority in satisfying the octet rule. So we need to give each fluorine 6 electrons so that the octet rule is satisfied. So we have used 12 to remaining. Whatever is left goes to the central atom and minus 2, 0. One, 2, 3, 4, 5, 6, 7, 8, 9. Should be 10. Let's trace back and see here, if we have sulfur in group 6, 6 valence electron, fluorine in 7 times 2 is 14. So if we add these two, give us 20. So if I have used here, we have used 16. So the 2 here, let's see how many domains, if it's gonna give us 20. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's giving us 18, it should be 20. Sulfur is in group 6, yes. Fluorine is in group 7, so we have used 26 plus 14 is 20. We have used 2 here. 2 and 2 plus 4. 20 minus 4 is 16. Yes, this is where I made a mistake. 12 minus, that's true. 12 minus, here is where it's messing up. 12 minus 16 minus 12, we remain with 4 remaining, not 2. No wonder why I was not getting the remaining electrons. So here, whatever remains goes to the central atom. So that if you look at the total number of electrons, valence electrons should be 21, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it should be 20. Each atom in the molecule, each atom in this molecule satisfies the octet rule. And the general formula here is A, P, 2, E, 2 with the general formula AP2E2 electron domain. Look at this geometry of the atom. This is the molecular geometry, by the way. It is pension. So this is and shape. If it was electron domain geometry, we talk about tetrahedral. So here for SF2 electron domain geometry. Electron domain geometry. Electron domain geometry is tetrahedral. But molecular geometry is panned, or sometimes this is V-shape. We say V-shape. Okay, you gotta look at the molecular for 3, I guess, right here. Tetrahedral for AP, it was AP2. You see, P bonding and then lone pair, it's AP2, and electron domain geometry is tetrahedral. You see, tetrahedral electron domain geometry. That's what I have here. Sorry about that. Electron domain geometry is tetrahedral, but AP2 pen shape. How I end up with that is because of this general formula I'm getting from my handout here, which I said earlier on, I will allow you to use in the exam or quiz to predict the molecular shape of either molecule or polyatomic ions. So for the tetrahedral, we have only one electron domain geometry to describe, but molecular geometry can be either tetrahedral if we have no bonding pair. All right, so here we can have molecular tetrahedral electron domain geometry. You can either describe that using either tetrahedral, or it can be trigonal, pyramidal. That means if you have a P3E1, that means there is a lone pair of electrons, or it could be pen-shaped, shape, which is equals to AP2E2, AP2E2, okay, AP2E2. Those are the molecular geometries for 4 domains of electron. In the bonding, in the following, we have 5, or rather, yes, 5 domains. We have looked at it, 2 domains, 3 domains, 4 domains. We're gonna go to 5 domains, but before that, let's look at the question here. The molecular geometry for this molecule is what? This is tetrahedral. Because of time factor, you usually end up with B here. That is tetrahedral. Please send me an email if you cannot figure it out this, and I'll walk you through on how to predict the molecular geometry for this molecule. For hydrogen, this for hydronium ion, all right? For hydronium ion, the molecular geometry for that, all right? Before we look at the 5 bonding side, the molecular geometry for that is trigonal, all right? This is trigonal. For HO3. Please try that and see if it makes sense that you are getting D. This is D right here. It is D. I meant to say D as in David. This is the molecular geometry. I didn't ask for electron domain geometry. I know you can do that. Before we look at the other one, let's see the effect of non-bonding pairs on the bond angle. We know that electrons are negatively charged and they tend to repel one another. The bond angle in methane, that means the angle between central atom carbon and hydrogen to hydrogen is 109.5 degrees Celsius. But if you look at the effect of non-bonding pair on the central atom, they tend to squeeze, they tend to repel. In other words, the decrease in bond angle has to do with the repulsion between the non-bonding pair or nitrogen for ammonia, the single bonds we have here. So non-bonding pair have effect on the bonding electrons. It's the same thing that the double bond and the triple bond, the electrons on the double bond and the single bond also do some repulsion. Look at the electrons on the double bond, they tend to squeeze these electrons, affecting this bond angle. That's why this one bond angle between chlorine is smaller than between chlorine and oxygen, because of this double bond, which causes the chlorine carbon to reduce compared to chlorine carbon oxygen. Bond angle is greater because of the repulsion. That's all you need to know, the effect of the lone pairs on the central atom and the effect of the double bond or triple bond. We have greater electron cloud in double bond compared to single bond, right? This leads us to looking at the other 2 domains based on the expanded octet rule, expanding beyond the octet rule. What does this mean? Some or elements on row 3 on periodic table, period 3 and below have expanded octet rule because of the D sub level, which can take up to 10 electrons. So sometimes you may end up with 10 electrons on the central atom. You may end up with 12 electrons on the central atom when you draw the Lewis structure, because of what? Because of the expanded octet rule. The result of these are two more possible electron domains, that is five. We call this trigonal power pyramidal for 5 domains, trigonal power pyramidal for 6 domain octahedral. We're talking about electron domain now. That if you have 5 domains, trigonal power pyramidal, if you have 6, it's octahedral. Well, if you have electron on the central atom, the first priority goes to the equatorial position. Equatorial position is along the equator, but this is axial position, up and above. All right. There are two distinct positions in this geometry. There is axial and equatorial. Lone pairs occupy equatorial position before, all right, the axial position. Explain that. So here are the types of molecular geometries, of course, for electron domain geometry. We talk about the trigonal power pyramidal. This is electron domain geometry for far. But for molecular geometry, it can either be trigonal power pyramidal, it can be seesaw, it can be T-shaped, or it can be linear. It can be linear. So don't think that always linear is for 2. We can also have 5 electron domain geometry, but the molecular geometry is linear. You got to follow your the rules for drawing Lewis structure for molecules. All right. Look at the electron domain geometry. We have only one definition, that is trigonal power pyramidal. Let me just blow up this, zoom this one out, so that you look at the electron domain geometry for 5 domains around the central atom, such as phosphorus pentachloride. You see 1, 2, 3, 4, 5 domains. If it is 4 molecules bonded to our central, 1, 2, 3, 4 with lone pair, the molecular geometry is described as seesaw, but the electron domain geometry is still trigonal power pyramidal. For 3 atoms bonded to central atom with 2 non-bonding pairs on the central atom, which if you look at, they occupy the equatorial position. Not the axial, they occupy equatorial position. This is T-shape, it's just like a T, you know, T-shape. This is T-shape. And then this is linear because of the equatorial position. These are the non-bonding 1, 2, 3. These are the non-bonding pairs occupying the equatorial position, and the molecular shape is linear. That's all for 5, which I believe, having gone through the 5 domains, you should be able also to extend it to what? Extend it to the 6 domains. Let's look at this question. Determine the electron domain geometry and the molecular geometry for 5, which I believe you can just go back to this. It's given here, all right? It is AP. If you draw the Lewis structure for that, the general formula for PCl5 it is AP5, which is 5 sides. And assuming it's in the exam or a quiz, and you're using my tables here, which I'll provide to you, it is AP5. And the molecular geometry here is trigonal power pyramidal, trigonal power pyramidal. It's the same thing as what we have, but if it was AP4E1, the shape is seashore, but the electron domain geometry is trigonal power pyramidal. It's the same thing as what we have here, that electron domain geometry is trigonal power pyramidal, and the molecular shape is trigonal power pyramidal for this question. Okay, you can do the same thing for octahedral, which you can define the molecular geometry as octahedral, square planar, square planar, square power pyramidal. These are the description of molecular geometries for six-sided steel extension for that. For long chain molecules, such as organic molecules with a long chain of carbon, you treat each and every atom individually. For example, here, this is CH3, COH, all right? So we only look at the carbon here and assign. We only look at this carbon. We only look at each carbon individually for a linear molecule. All right, let's see. In looking at the molecular shape and molecular polarity, all right, in describing the molecular polarity, what do we mean by polar? If a molecule, or rather, if there are polar bonds in a molecule, it does not mean that the molecule is polar. But we'll see in section 9.3, molecular shape and molecular polarity. Is the molecule polar, or rather, are electrons distributed equally in the whole molecule, or one portion of the molecule has high electron density compared to other region? In order to describe the molecular polarity, we need to understand the trend in electronegativity on the periodic table, which we covered in chapter 8, right? So if there are different atoms attached to central atom, they have different bond polarity because of the electronegativity. Carbon and carbon, all right, why do we say carbon dioxide is non-polar? Because there is equal pooling, or there is a net zero distribution of electron in carbon dioxide. The arrow you see here represent the force by which electrons are pulled between two atoms, or rather in just covalent bond, whether it is triple bond or single bond or double bond. Oxygen is more electronegative than carbon. Oxygen is more electronegative. Therefore, it's going to pull the electron in this side, it's going to pull the electron in this side, and there's an overall dipole moment of 0. We say the molecule is non-polar. It has to do with the trend in electronegativity. If you look at the H2O, we see the molecule is polar because of the net distribution of electron. Oxygen is more polar than hydrogen. Therefore, oxygen will pull electrons, and there is the overall net displacement in electrons towards. We say the molecule is polar. Chemists use electrostatic potential map to show which region of the molecule is electron poor and electron rich. The red indicates electron rich portion of the molecule. The blue indicates the electron poor region. This is electron rich, the red electron rich, because oxygen has more power, leaving alone hydrogen, they still electrons, but not as much as around the oxygen. If you look at the oxygen, why we have here red and this one red is because oxygen is more electronegative and we have high electron density around H oxygen. So that is how you look at the molecular polarity. In the lab, one of the lab, for those who are taking the lecture, there is a lab experiment where you will be required to state whether the molecule is polar or non-polar. You'll use the same approach. Use the periodic table. Trend in electronegativity. Look at the net displacement of electron and describe the overall dipole moment. Describe the dipole moment and say it's polar or non-polar. Last part in part A of lecture recording 9.4, 9.5 is part B, is valence, is on covalent bonding, the bonding theories. Remember what we said earlier on, there are two bonding theories. One is, all right, bonding theories. And you know, a theory is something, you know, you theorize that how is a bond formed? How are chemical bonds formed? We have just say, oh, okay, ionic bonding, transfer of electrons. Covalent bonding, sharing of electron. How are these sharing of electron take place, right? How is a covalent bond formed? Or first there is what we call the valence. VP stand for valence, all right? Valence bond theory, valence bond theory. And there is the molecular orbital theory. So when you prepare your own notes, bear in mind that we have two types of bonding theories. In the first one, which is 9.4, subject for 9.4 is that a bond is formed as a result of overlap of atomic orbitals. Overlap in atomic orbitals. For example, hydrogen, you have seen this in Lewis structure that a single line represent covalent, but how? All right, if each hydrogen has an electron, how are these electrons shared between the atoms? This must overlap. If you look at the overlap, the bonding theory, let me just start with this, that the first hydrogen and the second hydrogen, we have sharing of electrons, sharing of electrons. So here is where we have the covalent bond. This is valence shell or valence bonding theory, that there is an overlap. If you look at the 1s, 1s electron configuration, this is where we have the two electrons to form the single bond. If 1s and either 2p or 3p for chlorine, the two electrons for HCl, all right, hydrogen here, and then chlorine. If you look at the valence shell, you see this is the valence shell. Why we say 3p? Because the outermost electron is in the 3p orbital and there is an overlap. For chlorine, there is an overlap between 3p and, you know, the two electrons. So if I have Cl like that, for chlorine gas, chlorine gas, there is an overlap between so that the shared electron, this is covalent covalent bond, there is overlap. And in this case, the 3p here, which is the outermost, what the outermost shell for chlorine gas. This applies to other molecules that you need to draw the or write the electron configuration in order to see the valence shell, the valence or the outermost sublabel, see the orbital, how they overlap. This is atomic orbital, and when they overlap, they form a covalent bond. This is the description of covalent bonding using the valence bonding. By the way, when they overlap, there is an optimum distance which the two nuclei for atom should be separated within an optimum distance we call the bond length. Increase, all right, putting it too close will require a lot of energy. You see the energy too close, that means the radius between the two. If they are too far apart, no chemical bond. Too far apart, there is no energy and there is no full bond. There is an optimum radius between the two nucleus. Between the two nucleus here, this is what I wanted to show you, is that there must be a balance, the distance between the two, so that the sharing, this for hydrogen, 0.74 angstrom. I will not ask you, or no one will expect you to memorize the radius, the internuclear distance for all molecules, but understand when these overlap take place, there is an optimum distance in the nuclear distance for it to form. So remember the overlap, valence shell bond theory, okay, which is formed as a result of atomic orbitals overlapping to occupy the same space. In the next section, 9.5, we will look at the molecular. So far, we have looked at this. We will look at this in the next. I wanted to show you on my whiteboard that we are done with valence bond theory. In the next section, part B of the lecture, we will look at the molecular orbital theory and something beyond that. Other than that, please continue reading, make your own notes, and complete the online or MyLab and mastering assignment. Thank you.